So in this video, we're going to look at a couple examples of solving a second-order linear differential equation with constant coefficients. So that means that the equation basically boils down to this right here. And the assumption with an equation like this is that we can find solutions of the form y equals e to the lambda times t. So when we do that, we have to substitute it into the equation. So we have to find the first and second derivatives. And when we do so, we get this equation right here. Remember that it was equal to 0. And we can factor out the e to the lambda t. And since e to the lambda t is never equal to 0, it basically just gets ignored since our goal is to figure out what lambda has to be. And this equation right here turns out to be the ticket. This is what we call the characteristic equation, and it's going to tell us what the solutions to that equation are that will lead to the solutions to the differential equation. So there were a few different cases that I'm going to walk through as we see them as far as how the general solution goes. So without further ado, let's look at a couple examples here. So here's a differential equation, again, constant coefficients. So that means that the characteristic equation boils down to lambda squared plus 10 lambda plus 21 equals 0. And that equation, or that expression rather, easily factors to lambda plus 7 and lambda plus 3, which means lambda equals -7 or -3. So that means that since our assumption was e to the lambda t being the solution, this means that the general solution is c1 e to the -7t plus c2 e to the -3t. And that's all there is to it. So when there's two real solutions, the general solution is quite easy to come up with. So what happens when we have, repeated roots or imaginary solutions? Well, that's where we're going to go from here. So looking at number 2 here. So again, the characteristic equation just follows directly. That's lambda squared plus 4 lambda plus 8 equals 0. Now we might have to use the quadratic formula there because this doesn't factor. So we'll say lambda is equal to -b plus or minus square root b squared minus 4ac all over 2a, which turns out to be -4 plus or minus the square root of -16 all over 2, which is -4 plus or minus 4i over 2, which is -2 plus or minus 2i. So when that happens, the -2, as we call it, the real part of the complex solution, is going to be our exponential, and the 2i is going to be what our sine and cosine are. So this means my general solution is c1 e to the -2t cosine of 2t, and I just always put cosine first, don't ask me why, plus c2 e to the -2t sine of 2t. So cosine and sine always go together in the same general solution as we're seeing. So there's that general solution. Coming up to number 3 here, another one where, again, it's constant coefficients. So we have 4 lambda squared plus 12 lambda plus 9 equals 0. And this one turns out to factor as 2 lambda plus 3 quantity squared equals 0, which means we have a repeated root of -3 halves. So that's another special case. So again, remembering that the assumption came from being e to the lambda t, we know we can write c1 e to the -3 halves t. Turns out that the c2 also has an e to the -3 halves t, but to represent that there's a repeat, we multiply by t. Okay, so that is the general solution of that differential equation. I'll just put that in a box here so we have it. All right, and then last but not least, we have this one. So this boils down to 16 lambda squared plus 25 equals 0, which means lambda squared is equal to -25 over 16, which means lambda is equal to plus or minus the square root of -25 over 16, which is plus or minus 5/4 I. So that means that since this is a complex solution again, and remember this is really 0 plus or minus 5/4 I, That means our exponential is of the form e to the 0t, which is just 1. So that means this solution is not going to have an exponential term in it. It's going to be straight up sine and cosine. So that means my general solution is y equals c1 cosine of 5/4 t plus c2 sine of 5/4 t. And there we have it, the four main cases for solving a second order linear differential equation with constant coefficients. So there we have it. Thanks so much for watching.